Let's take a look at some applications of calculus to the sciences. Let's start with PV equals C. Okay, so what this basically states, this is from chemistry, is that if you have a gas at a constant temperature and you compress it, the pressure times the volume is always a given constant. Okay? So our question is going to be, what's the rate of change of the pressure to the volume? Now, whenever you hear the phrasing, rate of change, this should be a clue that we want the derivative, okay? Because the derivative measures the instantaneous rate of change, the rate of change at any given instant. So, in this particular case, we want to find how pressure changes in relation to volume. That would be dP dV. And we have choice as to how we go about this. Before we look at our options, let's just consider that we have PV and C up here. Now from a student standpoint, PV and C look like three variables. Now I'm telling you C is a constant in this case, but even if it wasn't, if you're just looking for the rate of change of dP dV, you treat everything else as if it were a constant, okay? Like C could be the number 3, I'm sure it's not that, but it's, some number. So, how do we find dP dV? Okay, two choices. We can differentiate straight out using implicit differentiation. That's a new technique we've developed. Why don't we start with that? Okay, so I have a product P and V. Okay, derivative of P is simply dP, right? So that we've got dP times V. By the product rule, I've got to add that to the second term. Derivative of the second term is dV, and that will be times P. So dV times P. And the derivative of the constant term here would actually be 0, right? Because it's a constant, it's not some variable. Okay, so I want dP dV, so now I've got to basically subtract to get it on the other side, and I get dPV equals dVP, negative, subtracting, and finally, doing the division, I end up with dP over dV equals negative P over V. Okay, so that is the rate of change of pressure to volume. Now, what if we did this in potentially a little bit of a more straightforward way, and we said, okay, I want to do it like this. I just want to say, it's a little easier to say, okay, what if I say P equals C over V, which is simply true. And now I can take the derivative of dP dV. Well, what happens here? Okay, well then dP dV equals, I guess like V to the negative first, so it's going to be negative CV to the negative second. And this is a little bit interesting because we have two different expressions here. And so how do we reconcile that? Well, first of all, it might depend on what the context of a problem and which one is better. But note that P equals C over V, right? We've got it here, it's in the original equation. So if we substitute in P equals C over V, this gives us the same result as it should, negative C over V squared. Okay? So this is a particular case where you certainly don't have to use implicit differentiation, but you could. Okay, next. Let's take a look at economics. So in economics, you might have what is called a cost function, okay? And what the cost function is, it's actually the amount of cost to a company that might be, say, producing some kind of a product, okay? So it's not how much it would cost in the store, it's how much the company would have to pay to produce it. And so C of X, okay, cost function, and there's not a universal formula for C of X. C of X is going to depend on, how big is the business, what are they producing, how much does it cost to produce, how many variables do we take into account. But these are often represented as polynomial functions. So let's just look at a sample polynomial function. Now let's say, okay, to get started with this particular product, you know, like you're gonna be looking at $2,000, and then maybe it goes up per product by something like 3x plus 0.01x squared. Okay, so there is a cost function. Now, c prime of x, okay, which is the derivative, is going to be called the marginal cost. And it's worth taking a moment to consider, what does the marginal cost actually mean? Okay, well, it's the rate of change of the cost, you know, it's like dc dx in relation to x, and x here is actually the number of products that the company is going to sell, okay? Now what's interesting about this is that in practice, a company is not going to sell a fractional part of a product, right? If they're producing blenders, they're going to produce like 1,000 blenders or 2,000 blenders, not, you know, 1,000.05 blenders. So if you think about c prime of x in this context, it sort of just means, okay, it's the rate of change of the cost at a certain amount. It's as if it's like how much the next one would cost. Now, in economics, marginal cost is actually used a lot because it's nice to graph, it's continuous, you know, it's smooth. So it actually is, you know, I'm not an economist, but I can tell you it is a thing that people use. And again, what I'm suggesting here is that it's a little bit different, because whereas like in a gas, you technically could have any value, you know, within like quantum limits, you know, these are going to be whole numbers. And let's explore it with an example. Okay, so what's the marginal cost at 1,000 units? Okay, I know I said 2,000, did I put up 200? I'm not sure. We'll leave it at 200, maybe I didn't. Okay, so this is some hypothetical product, maybe it's blenders, you know, we'll find out if what we put in makes sense. Okay, so we want to know, the question would be something like this. What's the marginal cost of producing 1,000 blenders? And again, what you need to note is that that means the rate of change of producing 1,000 blenders, which would be like producing more than that. So let's just try it. Okay, so what is c prime of x for this problem? Okay, the 200 goes away. That's like your overhead cost, you know, just producing any number of products. And then we're left with 3 plus 0.02x. Okay. And so note that that's sort of like the cost per blender here, if you like. I mean, the cost per blender is really here. It's not quite that. It's the rate of change. Okay. But it's like the additional cost, perhaps. So what is c prime of 1,000? Okay, well, let's check it out. We would get 3 plus 0.02 times 1,000. And that is going to equal 3 plus, well, for 1,000, I've got to move the decimal place 3 to the right, so it's 3 plus 20. And so you get $23. And again, what that means is each additional blender is going to cost you about $23 to build. Okay? Now, how much would the next blender cost compared to the first? You could actually put that into the cost equation. Okay? And that's another way that you can get that result. And I think this is just sort of worth looking at. So, right, how much would it actually cost to produce, say, 1,001 blenders versus 1,000? What is the difference in the cost? Okay? This is a way of computing, that's right, the way of computing a differential. 1,000, one more zero. Okay, okay, so this gives us the differential, the rate of, it's a way of getting a rate of change. So note that when you put in the 200 would cancel out, and you would be left with c of 1,001 would be 3 times 1,001 plus Okay, it's 0.01 times 1001 squared. Now, what is 1001 squared? I'll show you a little trick for this. If you do 1001 squared, okay, it's 1001 times 1001. Your first line, doing log multiplication, is going to be 1001. But then you'd be skipping over 2, and you just get 1001 again. So it'd be 100. Am I doing this right? You would normally skip 2, and I think you would start, yeah. You skip those 2, and then you start here. It'd be 1001. And you look at that, you get 1002001. Okay? Let's go ahead and just multiply it out. And so if we multiply that out, it's sort of a tedious calculation, but I do want to see how the results compare. Is that right? 1, 2, 3, 4, 5, 6. We do. Moving the decimal place over 2 now is going to make that 10,020. So, with a marker here, 10,020. I think I left off a 0. This is why scientific notation is useful, right? Because you can just not, you don't have to like, you put it in the exponent, right? Anyway, let's just go with what we had. 10020 minus, now we do this at 1,000, it's going to be 3 times 1,000. Okay, I'm just going to start to write it up, well, just that'll be consistent. 3 times 1,000, okay, it's 3,000. And then plus what? This one's a little bit easier because it's a square. It's going to be the same thing, but without the 20. Okay, so it's going to be 10,000. Okay, so what is the actual difference that we get here? Well, what do you know? This is like, okay, what is this? This is 3,000, and this is 3,003, right? So if I take the 3,000, I subtract that 3,000, those are gone, and I'm left with a 3, okay, combining these two. And furthermore, 10,020 minus 10,000 is 20. And what do you know? You get 23. Now, I did not use this 0.01, so technically, that 10,020, like the 0.01 would be there. So if you like, yeah, you've got an extra penny that you didn't take into account. Okay? So let's do another one. Let's look at physics. So many applications in physics. I think it's important that you start to get to know Isaac Newton's famous force of gravity equation. So what does the force do to gravity? Well, first of all forces in Newton are ma, mass times acceleration. More on that in future lectures. And the force due to gravity is written as usually G little m big M over r squared. Okay, so what is this equation? G is gravitational constant. And then it's the force between two bodies. Okay, so M is one body, little m, and big M is the other body, perhaps the bigger one. Maybe little m is the Earth and big M is the sun. Or little m is you and big M is the Earth. And then r squared is the distance between you. And by the way, if you're looking at where do you locate r for the Earth, it's actually at the center. So this is a famous equation, one of the most famous in the history of science. And we might ask the question, how does the force change compared to the radius? What's the instantaneous rate of change of the force as the radius changes? What's df dr? Okay, that's what we want. So we want to find what is df dr. And how do I tackle it? I got g and m and r squared. You treat the g and m, which they often are treated as constants. I say often because masses really have a rest constant. The theory of relativity actually adjusts mass based on how fast it's moving in relation to the speed of light. But it doesn't matter because if you want df/dr, you are holding those masses constant, okay? Whenever you take a derivative with respect to another variable, if you can have as many variables as you like, you're only differentiating with respect to r. So r is your variable, the others are just like numbers. So we treat this like a 1 over r squared. People call it the inverse square law because the square is in the denominator. We know how to do that. It's r to the negative second. And the derivative of that is negative 2 times whatever we have, which is gmm, all over denominators, well, it's r cubed, right? Because negative 2 minus 1 is negative 3. Yep. And so we get this. All right. R to the negative 2, subtract 1, we get negative 3. Okay? So, this is fascinating, right? We get like, that's df/dr. Okay, cool example. Let's do one more based on this changing mass I just mentioned. So, if you have a mass, okay, and looking at how it changes, this is actually, m changes. What you have is an original mass, m naught, and that's your rest mass. And it changes divided by this classic 1 minus v squared over c squared, which you see a lot in the theory of relativity. So what's what here? V is the velocity at which you are moving, okay? C is actually the speed of light. And again, m naught is your rest mass. So this mass changes depending on how fast you're moving in relation to the speed of light. So what is dm dv? How does the mass change based on how fast you are moving, based on your velocity? We know how to do this, okay? The only variable here is v, right? So we differentiate with respect to v, okay? The m naught is just stays there in the numerator, right? And we've got to differentiate the root. So we can leave the m naught in the top, and then the square root, well, it's to the 1/2 power, right? So technically it's negative 1/2 because it's denominator. So you bring the negative 1/2 down, so you get a negative 1, can stay up there with the m naught, 2, that's your negative 1/2. And then you end up with this 1 minus v squared over c squared, and it's all to the 3/2, okay? To the 3/2 power, because it's negative 3/2. And you're almost done, but not quite, because you also have to get the derivative of the inside. You have to get the derivative of the v squared over c squared. And so what's that going to be? Okay, well, it's actually, the derivative of 1 goes to 0, and then derivative of the negative 1c squared is going to come out, and you're going to get negative 2v over c squared, right? The negative cancels to make it positive. The 2 also cancels, and you're going to be left with your v, and all you need now is your c squared in the bottom, which we will put in place of this 2. Try to keep it a little clean. Erase the plus. We see that it's positive. And you have your rate of change of the math with respect to velocity. Now, what does all this mean when you're taking a calculus class? Okay, you're not expected to memorize science equations. Generally speaking, the equations will be given to you. So you might be given PV equals C. You might be given F equals GMM over R squared. You might be given M equals M naught over the square root of 1 minus V squared over C squared. You might be given a cost function C of X. You need to be able to know, based on the context of the problem, what you should be taking the derivative of with respect to what variable. Okay? You should also be able to interpret that problem, kind of like we did with the cost function. So the question could ask, what is the marginal cost of producing 1,000 units, and interpret it? And that would be kind of like what we did. So there's so many equations in the sciences that are widespread and used in calculus. And you'll definitely encounter, you'll encounter a fair share as you go forward.